Hello, today we are going to present in this webinar different tools and options to design nuclear power plants modeled with ANSYS Mechanical APDL. We will see two different main options. Some of them are for designing a new nuclear power plant, and the other tools and options are for designing for re-evaluation of existing nuclear power plants, seismic re-evaluation, that is performing a seismic margin assessment. We will see it later in detail. We are going to check and design a containing building for this webinar. Just for explaining all these capabilities, we will go through an example. And we will design a solid element model that is modeled in ANSYS Mechanical APDL. For this purpose, designing or performing a seismic re-evaluation, we will use these tools from CivilFEM. CivilFEM is a software that runs within ANSYS Mechanical APDL, and with a lot of tools for nuclear power plants. So, these tools that we will see on this example, the first tool will be the equivalent cell model. This tool, what it does is generating an equivalent cell model to the solid element model, and it will be used for checking and design to obtain reinforcement amount, cracking checking, all checking types we can perform. The target of this cell model is that the solid element results are stresses. This equivalent cell model, what it does is integrate those stresses, and then after integrating stresses on the solid element model, we obtain forces and moments. Codes and standards are based on forces and moments to calculate reinforcement amount, cracking, and all data. So we will have the option of performing an analysis on a solid element, this type of analysis, checking and design on a solid element model. Well, so first this equivalent cell model, then we will apply post-tension concrete tools, that is defining tendons, and CivilFEM will apply the equivalent loads, the equivalent prestressing loads to this solid element model. We will apply some other load cases, and then we will combine them. Also, we can combine with seismic analysis results, and then we will perform a ULS and SLS design and check. After this, we will follow all the procedure for a design of a nuclear power plant. We will perform the last analysis, that will be a seismic margin assessment of an existing nuclear power plant. That is checking the margin of the structure that can support a seismic event, and see the level of this seismic event that could be supported by this existing nuclear power plant. And after that, all of this will be performed in ANSYS Mechanical APDL, the classic ANSYS. And after that, we will see some tools, also CivilFEM tools for Workbench, for checking and design. Well, just for it could be a little bit confusing, but we will explain first what is CivilFEM. CivilFEM runs on ANSYS, but there are three different products. Just for you to understand, there's a CivilFEM that runs on MARC. MARC is a nonlinear solver of Hexagon, that is MSC software that belongs to an Hexagon group. That is a nonlinear solver, and CivilFEM runs on MARC. CivilFEM has its own graphic interface, and MARC runs in batch mode. That is one of the CivilFEM solutions. The other CivilFEM solution is CivilFEM for ANSYS Mechanical APDL. This is the solution we are going to see for this nuclear power plant design. CivilFEM in this case is an add-on on ANSYS. So what CivilFEM does is adding some tools to the ANSYS Mechanical APDL. So you are working on ANSYS, but with extra tools for nuclear power plants, or for civil structural geotechnical design. And the last CivilFEM products are CivilFEM apps for Workbench, which are ACT extensions. So you can design concrete or steel structures in Workbench with these CivilFEM apps. Well, who is behind CivilFEM? The company is in cyber, which is a specialized civil and mechanical engineering company, which has several branches. The main branch, which is about this webinar, is developing CivilFEM family products. Also, we are an finite element method software distributors. We've been working in this field for more than 30 years, and we are based in Spain. And other branches consultancy, also about finite element analysis for civil, mechanical, and CFD projects. And well, the last branch also we have is training. We perform on-site training for CivilFEM and also ANSYS and other products for different companies. We also support technical support from the softwares we distribute, especially CivilFEM. And well, that is one of our the company's keys, helping the customers for their models and giving a full service. And also we have a master, an international master of finite element method and CAD simulation with an open university and an e-learning platform about finite element. Well, this is a summary of the company and the software that is behind us, and we are going to focus now in these tools for nuclear power plant designs. Well, as I said, CivilFEM for ANSYS Mechanical APDL works completely integrated in ANSYS menu, in ANSYS graphic interface. So you can see that you have the classic graphic interface, and if you are running CivilFEM plus ANSYS, you will have some extra tools here. We will see some of these tools. Also, CivilFEM has some commands you can mix with ANSYS ones. So you are working like in one unique software, just ANSYS Mechanical APDL with extra tools. So well, CivilFEM has a lot of tools for many different civil, structural, and geotechnical fields like bridges, dams, tunnels, well, many tools, everything concrete or steel, any structure can be designed. And well, what we are going to focus is in the tools for nuclear power plants. Well, as I said, we are going to, in this nuclear power plant, we are going to, in a solid element model in ANSYS, CivilFEM is going to generate an equivalent cell model for integrating stresses from solid element and obtaining forces and moments. So we will be able to have in a solid element model in ANSYS stresses and all solid element results plus forces and moments in a dummy cell model. We are going to apply post-tension stress on concrete with tendons, seismic analysis, ULS and SLS design, and seismic reevaluation. Well, solid element model analysis, this is the model we are going to use. I'm going to open directly the software to see all these tools. So well, here we can see this is the model. Here you can see the solid element model. This is the mesh, and well, it is a containing building. As you can see, with well, lot of elements and just typical containing building. So well, first tool is generated the equivalent shell model. We can generate the equivalent cell model in just some parts of the model or in the whole of it. The way to do it is selecting just some parts of the model, in example the roof, the slab, different parts of the walls, and in that element selection we also select one of the exterior faces, well, the nodes of one of the exterior faces, and just with one command, or also with this solid to cell, just here new part, we select different parts and generate this equivalent cell model. I have previously done because I want to avoid running the software and spending time running and generating the model. And well, just here you can see the commands I have used to select this to generate this equivalent this equivalent cell model. What I've done is selecting different parts of the model and running this. Well, yes, you can see that the way it works is that first, from the solid element, CivilFEM generates in the middle of the section a dummy shell. This dummy shell is not structural, it's not adding structural, it's not adding any structural stiffness or whatever to the model. It's just some dummy shells to save forces and moments that we obtain from integrating. So the procedure is that when solving, the solid element model gets stresses. These stresses are integrated in these dummy cells in the normal direction to these cells, and then we obtain forces and moments, bending moments, and in this case out of plane shear. And then once we have in this dummy shell model, the equivalent dummy shell model, we get forces and moments. We can use those forces and moments to design and to obtain reinforcement amounts, and as you can see here. So well, you can see that after launching this macro, these commands, we generate, here you can see in purple, the dummy shells, and which are in the middle of the section of the solid elements. You can see here also for the slab, I didn't generate the whole dummy shell. I just generated in the inner part of the containment building. When launching those commands or generating the dummy cells, CivilFEM also generates some components for these cells to be easier to select or not. I've divided the model in different parts, and CivilFEM has created these components. First, the first component is just the foundation. Then I have created another component for the walls, other component for these buttresses. You can see there, just which has different stiffness, other component for ring on top, and the last one for roof. So well, here you can see the equivalent cell model that can be created in CivilFEM. If I plot the thickness, we can see that it's exactly equivalent to the solid element model. Oops. So we can have at the same time the solid element model plus the dummy shell, which is just working for integrating stresses and obtain forces and moments. So this is the first tool. Just for you to see how it works, we can just load one of the results we have, and one of the loads we applied. I'm going to use the next model, which is this one, and in this model I'm going to plot some results. Just what I have done is divided the model into different parts for the different loads that I have applied. So what I have solved is a few load cases. This is not a real case, this is just an example. For this target, I have solved some different load cases in different folders, and also I have solved them all together for ULS and SLS combinations and for seismic margin. So just for splitting all these tools and being easier to explain, I have divided it. I have several models for these tools, and then we will see at the end these combinations. So for the self-weight, which is this model, what I have solved is just with the acceleration, just vertical acceleration, y-axis, and just I have solved the model. So in the general post-processor, if I plot results, I have just one load step. So reading that load step, I can plot all solid element results. In example, vertical displacement, and well, this is the vertical displacement I get in the model. As you can see, it's about 2 centimeters on top. So well, this is the results ANSYS gives, and well, for plotting the CivilFEM dummy shell results, I have to select those components, the dummy shell components that have been created, which are these. And then what I have to do is just go to the CivilFEM part, which are these options that are added. Civil post-processor, from CivilFEM, I'm going to load the step results I would like, exactly the same as I do in ANSYS. And then I can plot, this is a cell model, so I can plot cell results. In example, I'm going to plot a bending moment about Z axis. Here you can see CivilFEM also adds just a symbol, which just explaining what we are plotting. Just also we have design criterion, positive bending moment around y-axis is this which has compression on positive part of z-axis. Well, here you can see bending moment, the bending moments we have due to self-weight. And well, if you see the macro I have launched, it is very simple, just solving acceleration, and CivilFEM automatically integrates stresses in these cells. So you have the advantages of solid element results with very detailed for different parts of the model, and also forces and moments to be able to check and design. So well, next tool is applying prestressed reinforcement tools on the model. So well, we have different ways, three main different ways to define tendons and to apply these tendons to the model. The most detailed one is through this tendon editor, which is a browser you open and just you can define by points tendons and just the layout inside the concrete walls. For this target, what you have to do is just perform different cuts on the model, and with these cuts, CivilFEM can capture the model from those cuts, and those cuts will be used for the tendon definition. In my model, I'm going to open the next one, this one. What I have done is just capturing different vertical cuts. These vertical cuts are captured here. As you can see, example, vertical cuts of the walls. The way to do this, I have here the macro, is just selecting with ANSYS commands, selecting a plane of nodes. You can see I just perform a cut in the wall, and just with this command, solid section, I just capture this wall, and then just clicking here, new solid, just I capture that tendon, that section, capturing different sections, just capturing these different sections just in all them around the containing buildings, in the containing building in vertical. We come after those cuts, open the tendon editor, and generate the equivalent, model. These are the vertices of the model. This is a top view of the walls. So we are going to define 4 different families of tendons. One of those tendons start from this buttress in this side that we use to pre-stress, and it will turn around inside the wall, all the wall, until the other side of the containing building, so it will cover just half of the containing building. So we will have 4 families, one that goes half of the containing building from this side, and the other will start in the opposite side of the buttress and will cover just the other half of the containing building. So for this target, what I'll do is first perform different cuts here in half of the model. Here you have the number of the cuts I have performed and define tendons through these cuts. So I will perform this procedure 4 times, one for tendons that cover this half, the other for this half, and just in the middle of, just we will repeat these tendons in the vertical direction, and also we will put in the middle of these tendons other 2 families that comes from this buttress till the other zone, and just covering the other half in this. So well, first just I have launched some macros, and the first is, as you can see here in this half, define tendons in this way. For that, after capturing those cuts, clicking here in the browser, as you can see, tendon editor, as after performing these cuts, we will have these cuts here have been captured. And also first we have this tab for the plan and elevation view. In this plan and elevation view, we define these tendons through points. So well, the way to define these tendons is in elevation view. Insert a point in example for this part in elevation view, and insert a point. Define the number of cut and the number of this point. Just in example, 0.1000. It will be in my cut number 1. I have defined different cuts 1, 2, 3, which is cut this one, so cut number 1, and just I set coordinates in y and y axis, and also for z axis and x axis for the different cuts. So in example, if I set y, which is the vertical, I set it to 1, it will place at height 1 meter. What I have done is repeat this procedure several times to place in elevation view all these points. Just I cancel not to create new points. So as you can see here, I have several points, 48 points, 1 every meter. So well, it has 46 meters height, this containing building, so 46 meters. And the same in plan view. In this plan view, I can add here, insert a point, and I can add several points. In this case, I have only just 14 points, just on plan view, 1 on these sections. So if I zoom, I start the buttress just through these points. So well, just once I have defining points in plan and elevation view, the next step is insert a tendon. So well, I could click the right button, insert a tendon, and tendon number, example 50, and just I define pre-stressing steel material, areas, and so on. So well, just after defining this tendon, I will click through plan and elevation view the points it goes through, and with this data, just I will define these lines and will define completely my tendons. Also, I can check these tendons in the cross sections, just tendon by tendon, tendon 1, 2, 3. Well, they are here at the bottom. You can see 1, 2, 3, and well, they goes through different points on plan and elevation view. And well, just I can check it through different cuts. Well, after defining all my tendons, next step is calculating losses. CivilFEM calculates automatically all losses, short-term and long-term losses. Just we can calculate them clicking here, and just we set time for these losses. That is we can calculate for day 0, so it means we are CivilFEM is calculating only short-term losses, elastic shortening of concrete and friction, And well, long-term losses, we also consider creep, sink rates, and steel relaxation. And also for short-term losses, just CivilFEM calculate the slippage, the losses due to the slippage of the anchors. And well, just click, once we set here time, I just click OK, and I calculate, CivilFEM calculate these losses. I could also save these losses, read from a file, and edit them. So in case I prefer to apply other losses different that CivilFEM calculates, I can modify them. And well, after defining all my tendons, as I said, I'm going to define four times these tendons, 4 families, one of this half. Just next step should be apply to load these tendons. Just clicking here in this part, I will load, CivilFEM will apply the equivalent loads to these tendons to the model. Just well, how does it work? What CivilFEM does is first to obtain the intersection of the tendon through its element. So this is a solid element, and CivilFEM calculates point 1 and point 2, which is the intersection. Then CivilFEM, after calculating from pre-stress force that the user set, CivilFEM calculates stresses along all the tendon considering losses, and just in these 2 intersection points, CivilFEM has the force at both ends of the tendon. So well, considering these 2 forces in this element where the tendon goes through, what CivilFEM does is applying equivalent forces on the 8 nodes. So in the 6 directions to pre-stress this element in the same way this tendon would do. So well, this is very useful because these tendons are completely independent of the mesh. The layout could be completely independent, and CivilFEM applied equivalent pre-stresses through all the elements this tendon goes through. And this works for beam, shells, and solid elements. In this case, I'm working on a solid element model, so these loads are going to be applied on this solid element. Also, very important, losses. Just CivilFEM calculate losses through tendons considering the layout, the friction of the layout, considering the length and also the angle of when it's not straight tendons, long-term and short-term losses. And you can plot in this browser, you can get on every cut of the model, you can get losses and total forces. This is the total force of the model and the losses that has been calculated by CivilFEM. Well, this is a way to generate tendons. Other way to generate tendons is through lines. With that other tool, just capturing cross sections, I've defined circumferential tendons in all the walls. There are another family tendons, which are the U tendons, which grow from one bottom of the slab through all the roof and just go down to the other side. It's like in an inverted U, these tendon shapes. And there are like 2 groups, one in X and one on Y direction. The way to work with this tendon tool is just selecting from the model. For explaining this part, I have this other model, so you can see this is the tendons and this is the elements. So well, for these tendons, I have also this group of lines. I have created a component for every of these lines that you can see here with the tendons from tendon 1 to tendon lines. These components, well, you can see here with this have this U shape. You can see here several U tendons. So well, what I have done with a macro, as you can see, I can mix ANSYS and CivilFEM commands. For the U tendons, I have with this macro created a loop. Just I go for tendon by tendon line, selecting them, and with this command I generate a tendon from this line. I give a prestration force, initial point, and different data for losses calculation. Just I have created in this way 80 tendons, and after that option generated, converting these lines into tendons, I can load the equivalent forces. The way to load these equivalent forces is similar. It doesn't depends on the way you define the tendons. The algorithm to apply the equivalent loads is exactly the same. It doesn't matter if you have defined the tendons with the tendon editor and that layout, or with these lines. CivilFEM calculates in the same way equivalent forces and apply to the model. So well, I'm going to load this command to apply the equivalent forces of this. And now, well, you can see CivilFEM is calculating these equivalent forces and will apply these equivalent forces to the model in this U-shape model. You can see here the first U tendon, second U tendon, and well, just the order of these loads can be also defined. As this is equivalent forces that you are applying to the model, these forces can be solved apart in different load steps, can be combined, and also if you are performing a construction process, well, you can also add these forces, combining the construction process and just the element activation and deactivation of different parts with these tendons, so you can perform a very detailed construction process. Well, you can see CivilFEM is applying all these equivalent loads. Well, just I'm going to continue. Just after applying these loads, you can solve and you can get the next load step. This is the tendons. You can see. Well, I have two different tendon groups. One circumferential, other with U. They applied equivalent forces, and we can solve it. So well, I have split it into two different load steps. One for circular, one for vertical. I could split in several more or just put them together. Next step is the seismic analysis. Well, for the seismic analysis, you can perform the seismic analysis in the way you could like. That is with ANSYS response spectrum analysis. It's okay. CivilFEM works on ANSYS result file, RST files. So just reading those results, example stresses from those result files, integrating those stresses to create the equivalent forces and moments in the dummy cells, and checking. So it doesn't matter how you perform your seismic analysis. You can perform a seismic response spectrum analysis with ANSYS, also transit analysis with ANSYS, or import it from a third-party software. Just if you SASI, any other software, if you perform the seismic analysis with that software, then you import those results into a RST file, and CivilFEM can integrate those stresses as well and obtain the equivalent stresses. So that is very simple. And well, very important, after you perform your seismic analysis, in example using the response spectrum analysis, you will have just in absolute value forces and moments, because you have combined them, and you know results from seismic analysis, response seismic analysis are in absolute value. So well, just if you combine it with ANSYS, you can have all positive, and you can just multiply by -1 and have all forces in negative. In example, axial force and bending moment, both positive and both negatives. This is the typical procedure, just if you don't have CivilFEM. So if you design for these forces, you will have this interaction diagram. If you design with CivilFEM using only this seismic result for ANSYS, you will have all positive, which will be this result, and you have this interaction diagram designing for these results, and all negative, which gives you this other value. So designing for these two options, well, with this section will be okay. CivilFEM gives you, with this seismic sign utility, to combine this seismic result, as I said, from ANSYS response spectrum analysis transit, or for a third-party software. If that is in absolute value, CivilFEM gives you the option to combine with the static combination, the seismic results in axial force and bending moment, all positive, all negative, and one positive and one negative. With these 4 options, we can see that axial positive, that is tension, and bending moment negative, we don't, with this option, the section that was designed for positive and negative, all these values, it doesn't fulfill for this combination, positive and negative. It's outside. For negative and positive, it's inside. It's okay. So just we are not covering with that combination. Just combine it only with ANSYS. We are not covering this option, which is much more unfavorable. CivilFEM gives you this tool to combine the 4 options. So we are in the security part using CivilFEM for this combination. Well, this is one tool for seismic analysis, just splitting the seismic result you read from ANSYS or from other software. You read them in absolute value. CivilFEM split it into 4 results, combining positive, negative, and positive and negative both in this part. So well, then we split the seismic result into 4, and then just we have to combine it with the static results. Well, for that, just I have here another model, which is this. Well, we can see here all the tendon forces in the model that were applied previously, that it has finished, and just we could solve it. Now let's go to combinations, and well, we can see in this model that we have solved several load steps. We have 10 load steps that we have solved it. Let's see the macro for ultimate limit state combinations, and we have solved it just these 10 load steps. Just this is a simple example just for you to see. So what we have solved it is self-weight, which is just acceleration, vertical acceleration, and we have solved it. Then we have solved the C tendons, the circular tendons, the horizontal ones. We have also solved the U tendons that we have seen, and then we haven't seen this part, which is applying dead loads, inner pressure, summer and winter temperature, the gradient on the walls, wind, and 2 seismic levels, OBE and SSE. So we have solved this. I have solved in the model these 10 load steps, and what I'm going to do is define different combinations with CivilFEM. Here I have the combinations we are doing. The first combination is adding. With this command we have self-weight plus dead loads. We combine them together. Then temperature, which is one or the other, so combination rule is option. We could have only one of them, and then once we have the self-weight plant over dead loads and temperature combination, we use that combination for combine. This is by commands, and we also can use that previous window. So well, just coming to the model, if I launch these commands, I have defined my combinations. Also, these combinations can be defined here, combine results. Combinations, also you could combine with ANSYS if you prefer. Just what we need is a result file, just a load step, just to read and to check. But for you to see these tools, I have created here with this browser. It's very easy to create combinations. I have created a first combination, which is the addition of self-weight plus the overloads. A second combination, which is the temperature combination, and so on, the loads and so on. I have created these combinations. The way to create a combination is very easy. Just I'm going to create a combination ULS 3 in example, and I create just I said here which is the addition, and just let's check ULS 4, and I create this combination. The number of loads that I would like to have, the load steps in example 5. Click here, create. 5 created, and then here what I can do for these combinations is to take load steps from here. This will be the combination of load step 1, 4, 6, and 8. In example, I just put them here, and then I can add different coefficients, different coefficients for the different loads. In this way, I create my combinations, very easy, combining load steps and also previous combinations to nest these combinations. After that, I click here, OK, and I'm not going to save this change. And after that, I just combine all load cases, and after combining, I can check and design my results. Well, for checking and design, I need my dummy shells. So I'm going to select just the dummy shell model. And here I have the dummy shell model. Well, just I have different combinations. The result summary, you can see in my case I had solved 10 load steps, and I have created 2 different combinations, 2 ULS combinations. I could create several, and then I will have several extra load steps that are generated by CivilFEM. So well, I have to read first one of those load steps, which will be load step 11 in example, and after reading it, I get forces and moments. I could plot. In example, I'm going to plot forces and moments, the bending moment Y for that combination, and then I can design this combination. Well, as I said, there are several elements, so it takes just some seconds to load them. So all this result that I have loaded correspond to one of the ULS combinations. I'm going to just load it and then to design by code. Here you can see that the ULS combination with the title is self-weight plus test load plus tension forces plus wind plus temperature. I can add several combinations with the seismic loads and all this data. So well, here you can see the bending moment around x-axis. Also, I could generate any of these axial forces, sliding shear, any of these forces. I can plot them and just list these results, also export. And last is code checking and design. For code checking and design, I have here several codes I can use. Just by default, we have here the Euro codes, but I'm going to use in this case the ACI 349 13 edition. We have, as you can see, several international codes, Euro codes, ACI 318, also British Standard, Australian, Chinese, Brazilian, well, many codes. For taking this case, just for the ULS, I'm going to use the 349 from 13 edition, which is a nuclear code. Well, after selecting the code I would like to use to check for the post-processing, I should perform here code checking. For the ACI 349 for concrete, I also can check steel. I selected Eurocode 3 for steel. I can select any other code for steel. This is a concrete model, so only concrete checking. I can check or design. Check is that if I define my reinforcement, well, in these dummy shells, I can set my reinforcement groups. If I define my reinforcement group, I can check them if that fulfill the codes or not. Or I can design. For designing, what CivilFEM does is calculating reinforcement amount. I can design for bending plus axial, for out of plane shear, in plane shear, and well, the CAB method, which is the tie and strut method, which combine all forces at the same time and calculate all forces. Well, there are several methods. If you are interested, we can explain in detail all these methods, but for this 45 minutes webinar, we just have time for an overview. But in example, I'm going to perform in plane shear checking. In plane shear, I click here and I have this browser with all for this update code ACI 349 from 2013. I have to select different design options that depends on the different articles of the codes. There is different formulation if I'm checking walls or slabs, and if they have seismic loads or non-seismic loads. This is walls with non-seismic loads, just this combination. Just the type of analysis. Well, also we have to select if we are in other causes or we have joint strengths. Also the vertical axis, because well, just for wall designs, the vertical axis is treated in different way for bending moments in the vertical axis. And also I can limit the stress on steel for my design. Instead of being the J limit, I could define a lower limit for the steel. Just clicking OK. CivilFEM perform the concrete design calculating reinforcement amount. Just as I said, I can do this procedure for bending plus axial, for in plane shear and out of plane shear. And after designing it, here I just can graph results. And for in plane shear, in example, I'm going to plot reinforcement amount in X and Y direction. Click OK. And plotting this result. And well, CivilFEM not only calculates reinforcement amount, also all intermediate values that are needed to calculate this. Just after plotting this, I can show you different results we could plot. So well, here you can see this is the area per the unit length of in plane shear reinforced in X direction. The direction X or Y direction are the element axis. If you would like the shell element axis, if you would like, in example, to have in the dome of this circumferential and radial reinforcement, you should reorient the shell element axis just in that direction with just placing a local coordinate system, a cylindrical one here or a spherical one. You reorientate element axis in those directions, and then CivilFEM calculate reinforcement amount in those axes. So well, you can see you can plate the CivilFEM result, which are this concrete contribution, steel contribution, also just the in X and Y, and reinforcement amount X and Y and total for this checking type. You can see here the results. The results are in the units, which are meters, in square meters per meter, just for of in plane shear reinforcement. That it could be just about 80 square centimeters per meter in the bottom, which is the highest part. The bottom is delimited by the minimum reinforcement. It has 3.5 meters thickness, so the minimum reinforcement for considering that thickness is high. And in the walls, this result is due to the forces and moments we have. Well, the in plane force. Well, just here I have some plots of typical results, which are for this ULS check, which are reinforcement amount for bending in X direction top, a Y direction top as well, and just this in plane shear. So well, these are the typical results. CivilFEM gets reinforcement amounts in this dummy shell equivalent model, which obtain forces and moment from integrating stresses. We also can perform SLS design. I have this other model. In this case, what I have done is using just the Eurocode 2 for calculating these results, and also well, just I have performed the equivalent combinations. I'm going to see the just SLS design. I have applied this equivalent combinations, but with different factor. If I load it, you can see here combined results. So well, I have here equivalent combinations, but well, just the coefficient is depends on what I'm combining is 1. Here you can see 1 just for tendon 0.9. Well, I have different coefficients for the combinations. And also, well, I should perform here code checking, Eurocode 3, check, and now cells and checking for cracking. Just, well, for checking for cracking, I should set the maximum crack width 0.02 millimeters, the 0.2 millimeters, the maximum crack width. And well, for calculating this crack width, I need to know for checking this and calculating this crack width, I need to just to set my reinforcement amounts. So for this case, for cracking checking, just in the different dummy shells, I have creating different cross sections. For the dummy shell group 1, which is the bottom part, I have set here my bending reinforcement. My bending reinforcement is 32 millimeters thickness bars every 15 centimeters in X top and bottom. With I have set here a mechanical cover of 5 centimeters in all directions. Well, this is just an example, but it cannot be true. I could add several different mechanical covers, 6 centimeters in top, bottom, just considering thickness. So I set different. Also, I can set shear reinforcement and in plane shear reinforcement, and I can check it. For cracking checking, I have set my reinforcement groups in all the zones, and then I have performed this cracking checking. I'm going to show just these results. What I have is crack width in this direction, which is 0.37 millimeters. It means in these zones, crack width is over the limit of 0.2 millimeters. So well, I could modify my reinforcement and check again. It's just plotting the model. I can see that I could graph in my model, which is this one. You can see here that I could graph different results from cracking checking. These results are just crack width, and also I can plot maximum stress in concrete and in steel. It's very important because it's not just for cracking checking, it's not only limited crack width, but also compression in concrete and tension in steel. You have to fulfill those three, well, depends on the AFTID code, in this case for the Eurocode, but depends on the AFTID code, but for the Eurocode you have to fulfill compression on concrete, tension on steel limits. There are those two limits, plus crack width, that is the third limit. So well, you can plot also here the stress in concrete, the stress in steel, and crack width. Just with those results, just you can design your reinforcement. If it doesn't fulfill those data, you can modify your reinforcement amount and just continue. Well, I have not much time left for this webinar. I'm going to go faster through the next tools we have. The next one is based on all existing nuclear power plants and how to perform a seismic margin assessment. It is based on this HCLPF concept, which is the high confidence, well, I don't remember very well the name, which is a little bit confusing, and high confidence, low probabilistic of failure, HCLPF. And this is based on this code, APRI MP6041, revision 1, which is based on this formula. This formula said that the capacity of the section, subtracting the demand of the non-seismic loads divided into the seismic loads demands, gives you a factor. Just for easier explanations of this, is that if you have in this vertical axis, you plot the demand, that is the forces you have in your section. If you have the non-seismic combination, the demand, in example, a shear force equal to this value, and you know the capacity of the section is this line, the shear capacity of your cell could be this value, and this is the value due to non-seismic combination. If you apply a seismic analysis, a seismic load, which could come from this pink spectrum, could come from any other type of seismic analysis, gives you the addition of those, which is this point. So it means with the non-seismic loads plus seismic loads, you have this shear in plane shear force, in example, which correspond to this seismic level. In the horizontal axis, we plot the seismic level. So just if we increase this seismic level, we increase this line until capacity is equal to demand. That is the failure point. So the failure point gives us a seismic level. So well, what this tool is doing is calculate the factor of this peak acceleration ground where the failure could happen. Basically, CivilFEM calculates the capacity of the section, the part of this capacity that is consumed by the non-seismic loads, and then the seismic margin with the rest of the capacity less the non-seismic loads, and just calculate CivilFEM the seismic level that generates the failure. But well, this is for understanding, this is done with linear analysis, but CivilFEM doesn't do it in a linear analysis, because CivilFEM also considers nonlinear section capacity. That is, for example, the capacity for bending moment for the Eurocode formula. The capacity of bending moment depends on the square of the axial force, of the shear, out of plane shear force. So if we increase the seismic level, we will increase this shear force, so the bending moment capacity will be reduced by the square of the axial force. So well, the demand is nonlinear, and also the capacity consider all forces and moments at the same time. So CivilFEM increase all forces and moments at the same time from the seismic level. They consider nonlinear capacity of the demand and calculate this failure value just without just with a nonlinear behavior of the capacity of the section, and also increasing all forces and moments at the same time, and calculating the failure depends on what happens before of the combination of forces and moments. So well, it's done in a very accurate way. And these are some typical results. I'm not going to show the model because just I have spent a lot of time. So all typical results for seismic margin assessment is giving you on the steel model. These are steel beams and columns or concrete, and gives you different seismic level, just in terms of G, just the peak ground acceleration, where failure will happen. So you have different seismic margin and different plots. And well, just now we will have a fast overview of of how CivilFEM would work in the Workbench environment. Alberto will explain, that is my co-worker, we will explain how to use these ACT extensions that works on the Workbench environment. If you have solved your model in Workbench, you can also use CivilFEM tools for check and design by different codes. So Alberto can continue now.
Hello, my name is Alberto. I'm going to perform a design analysis with the ACT extension CivilFEM with ANSYS Workbench interface. So first we have to know is to manage the extension of CivilFEM in the Manage Extension menu. So we have to activate this extension, and after that a box will appear in the bottom part of the ANSYS Workbench interface. So we have to enter this box in the model. We open the model. Once we have the model, we can see we have performed 3 loss steps, X, Z, and Y, with a different acceleration per X. And after this, we can see in the bottom part the check and design box. We have the ribbon in the top. We create the CivilFEM tree. We have the codes in order to check this the steel code and the reinforcement code. We will use the nuclear concrete reinforcement code. First, we create the concrete material, an ASCII material from the ASCII code, and reinforcement steel material as well. This one, for example. We can modify any property from code from these materials, as well in the steel reinforcement, and we can create the cell structural element. Selecting the material, we can perform any property from bending, shear, or impedance shear reinforcement, but we are carrying out the bending reinforcement, the mechanical cover, but no reinforcement because we have to design the model. So we select the geometry, in this case, the face, the cell. We can modify any property we would like to change. No one is modified. Next step is to fill with load cases the dataset. After this, we can create the combination by modifying the menu. We create the combination with number of load steps we would like to take into account. 3 gaps, 3 load steps. We accept. And after this, the next step and last is to create the design analysis, arbitral frame 1 with the X-stop result. We check and CivilFEM is solving. We can see the result in here with 80 square centimeters per meter.
And well, now we are going to have a fast overview of the case studies. We have several clients that are already using CivilFEM. Here you have some of them: Arriva, Atom Project from Russia, United States, Westinghouse, Siemens. Well, some of these clients, and we have some case studies they have provided us, just for you to have some examples of what it is being done with CivilFEM. These neutrons from science did a study of just the restoration project of just seismic reevaluation, and well, for this purpose they calculate needed reinforcement amount with CivilFEM, just considering these results, just the seismic, just using this tool for axial and bending moment, all positive, all negative, combination of axial, positive, bending, negative, and the opposite. So to cover all the options, these 4 options, they use this tool, and also code checking and design. This other case study, this was we did this in our consultancy department. It was an all nuclear power plant. They needed to perform a cut just to change the reactor renewal. So what we did is cutting the tendons, just adding new concrete and new tendons on this model. So just in this case they were helicoidal tendon, and what we did is perform the construction process of the, as it was done at the beginning, then remove these tendons, that is removing the pre-stressing loads, removing this killing these elements, aliving new elements with new material, and pre-stressing again, and we calculate reinforcement amount. Other case study, this is a turbine foundation, and also reinforcement amount were calculated by Siemens. Westinghouse also used for a similar model. Arriva has been designing last years. Arriva USA in Charlotte, North Carolina, has been designing a new model, a new nuclear power plant model. And this containment building, just using ACI 349 and ACI 359, that are 2 nuclear codes. And well, this is a plot of the model. And also Enginsoft in Italy, they perform, just with our help, they perform in an all nuclear power plant. They calculate the seismic margin assessment of this nuclear power plant that had an auxiliary building plus the nuclear power plant that had 2 reactors, and perform in an all nuclear power plant due to the crisis that we had in the nuclear power plant field after Japan disaster. They reevaluate this nuclear power plant to check if this nuclear power plant was safety or not, with a new seismic level that was reviewed after that crisis, and it was used to check the old model and to obtain the seismic margin that nuclear power plant still had. And well, as a summary, you can see we can, in a solid element model in ANSYS, we can perform we can obtain the equivalent cell model, apply post-tension loads, seismic analysis, and design by code, and also perform a seismic margin assessment in an existing nuclear power plant. And also, this is for classic ANSYS mechanical APDL, and also we have some tools in Workbench for checking and design. Also, we have a nuclear power plant quality assurance system that we fulfill with the Nuclear Regulatory Commission just for this quality assurance system, just for being able to work in the nuclear industry. And at the moment, we are performing different improvements. The Russian code, we are improving it. We had a previous version, but we are adding for concrete cracking checking and improving and having some other articles we didn't have. And also from the ACI 349, we are in the process of developing the reinforced concrete design considering thermal effects, that is, considering the cracked section inertia, the cracked section properties. And also we are open to develop any other tool you would need under demand for Workbench and also for CivilFEM. Well, if you would like more info, you can get in the company website, cyber.com, or also just about the software's website, which you can get much more information, civilfem.com, or you can find us also in the social media. So thank you very much for this, for the attention of this webinar, and just hope you found it useful. I've seen you were asking me some questions using the chat. Well, you are too many. I didn't have much time for answering, but just I will email you with all this information. Also, if you would like a special demo, get more info about what we do, just don't hesitate to email us and to ask for extra information. Thank you very much. Bye.